Okay, welcome back everyone. We're going to continue our discussion of momentum by talking about the very important concept of center of mass. So what we're thinking about here is what is the center of mass of a system and how can we use it to more easily solve momentum problems. So the center of mass of a system is the point at which you can pretend like all the mass is residing. And mathematically, we think of this as a weighted average. Okay, so when you have a system that's an assortment of particles or a system that is a solid object, we can still calculate a weighted average for each. So for a system of points, the x-coordinate of the center of mass is the sum of the product xi mi over all I divided by the total mass, which could also be written as the sum over all I of mi. Okay? Similarly, the y center of mass is the product of yi mi over the total mass, and similarly for z. So it's a weighted average of the positions. And depending on what you've already seen in math class, you can actually do this for many different functions. Not just the mass or the location of the center of mass. Okay? And there's also analogous equations for velocity and acceleration. So if you take dx dt and you take that dx dt, well, now you've got velocity of the center of mass of the x-coordinate. Okay, so there you go. Vx center of mass would be dx dt. All right, so how do you find the center of mass of this? Well, x center of mass is going to be the sum over I of xi mi over the sum of all I of mi. Okay, so basically what you do is you take each object, you multiply its mass by its position, you divide by the total mass. Now the total mass in the system is going to be 6, so let's check this out. Okay, the 2 kilogram particle is at a location of -1. Okay, so what I'm doing is I'm doing the mass and then the position. Okay, the 1 kilogram particle is at an x position of 0, and the 3 kilogram particle is at an x position of 2, and that's all divided by a total mass of 6. So the x center of mass for the system will be 6 minus 2, which is 4 over 6, or 2/3. The y center of mass is the exact same calculation. It's the sum over all I of yi mi divided by the sum over all I of mi. Okay? So that's going to be 2 kilograms times 2 meters for the 2 kilogram guy up here. And then we'll have 1 kilogram times -2 for this guy here. And then we're going to have 3 kilograms times -1 for this guy right here. So you can probably tell that most of the stuff in this system is below the y equals 0 line, so we're going to have a negative y center of mass. So that's going to give me 4, a -2, a -3, so I'm going to get -1/6. Okay? Alright, so it's kind of like the 2 kilogram, even though it's not as heavy as the 3, it's up higher, so it's got more weight to its position. Okay? So the center of mass for this system would be 2/3, -1/6. Okay. Now what if you have a solid object? Well, it's got cut off a little bit, but I think we can tell what's going on. If the object is of uniform density, you use the geometric center of the object. If you have a combination of objects, you pick the center of each part, and then you treat that center as a point. Okay, so for example, this donut right here would be composed of a positive circle, and then we would subtract from that the smaller negative circle. Or up here, with the circle and the rectangle, we would just add the center of masses for each of those objects. Okay, so here's an example. Determine the center of mass of this shape. Okay, well, first of all, if you think about this, the area of the big one, if it was completely filled in, would be pi times 2r squared, right? So that would be what, 4 pi r squared? And the area of the small one would be pi, and it looks like it has a radius of 1r squared, so that's just pi r squared. Now, we're just going to say that the whole has a negative density, so the whole is going to have a mass equal to negative m, but the solid part is going to have a mass equal to plus 4m. Okay, and the reason for this is that the mass is going to be proportional to the area. Makes sense. Okay, so the center of mass of this, I think we can see easily that we don't need to calculate the y center of mass. It's just going to be 0 because the center of masses of each of these objects are at 0 on the y-axis. But x center of mass will be the sum over I of xi mi over the sum of all m. Okay, so we'll take the whole. Now the whole has a center of mass of negative r, but it's got a mass of negative m. Make sense? So it's at a location of negative r, but it has a mass of negative m. So that's this circular hole right here. And the solid part has a center of mass at 0, and it's got a mass of 4m. Now you need to pretend like the solid part is actually a complete circle, and it has stuff sort of behind this hole. So really what we're doing is we're doing like a solid plus a negative hole. Not sure if that makes sense, but the hole is like right there. Okay, now we divide this by the total mass, which would be 4m minus m. It's weird to think of negative mass, but that's how you treat a whole. And that's going to go away. You're going to get mr over 3m, or in other words, you're going to get that this has an x center of mass of r over 3. And so that's going to be, if that's 1r, it's going to be about right there. Okay, so the effect of the whole means that the center of mass shifts to the right because there's not any stuff in the hole. Okay, but it's not a very big hole, so you still have a lot of stuff that's far away, so the net effect is it goes to r over 3. Okay, now the last thing is how do you deal with more complicated situations? So if you have points or simple geometric shapes like we've been talking about, then this is the equation for center of mass. But anything more complicated than this, and we have to do an integral. So instead of splitting it up into a sum over I of xi mi, what we're doing is we're taking it and splitting it up into a bunch of small masses, dmi. And when we take the sum of those, that actually turns into an integral. Okay, so let's look at an example of this. Okay, find the x-coordinate of the center of mass of a rod of length L whose mass per unit length varies according to the expression lambda equals alpha x. Okay, so this is the first time that we've seen this, and so this is a linear mass density. This is a linear mass density, mass per length. Okay, so lambda is defined as mass per length. All right, that's also dm over dx. So if I take a tiny little chunk here, it's going to have a density of lambda. Okay? Now, the reason that this is getting introduced now at this point in the course to you is that we're going to be using the idea of linear mass density a lot. We're also going to be using surface density, sigma, which is like mass over area, And we're also going to be using rho, which is a volume mass density. So mass per unit volume. And you're going to be seeing those a lot, especially if you continue to the E&M semester of the course. They are everywhere in calculating electric fields, potentials, magnetic fields. You're going to see this sort of thing a lot. And the other calculus tool that's very useful to us is saying that the center of mass is the integral of x dm over m. Okay, so taking a tiny bit and integrating it, and we're going to see this actually next unit, where we can find a value by integrating a small piece. Okay, so let's set this up, and basically what we want to do is we need to get rid of this dm here. But what we notice is that in our definition of lambda, that lambda is dm dx. So this means that x, center of mass, is equal to the integral of x. That's just a variable that's there in that equation. But then dm is going to be equal to lambda dx. And then that's all going to be divided by the total mass m. Okay, so we're going to come back to this. All right, come back to this m. Okay, we can write it as 1 over m times the integral of x times lambda, but lambda is alpha x, and that's dx. Now we're also going to be integrating this. Now that it's with respect to x, we're going from 0 to L. So those are the limits on the integration. So x center of mass is 1 over m, integral from 0 to L of alpha x squared dx. Now this is a pretty simple integral to do. We have 1 over m, and then we're going to have alpha x cubed over 3 evaluated from 0 to L, which is just going to be 1 over m times alpha L cubed over 3. So that's x center of mass. Okay, but there's one more thing that we can do. We know that lambda is actually equal to the total mass over the total length, and so we can get rid of that in this expression if we want. And so this is one way to write it, okay, but we could also say that this is equal to alpha L squared over 3 lambda, and that's just because lambda is m over L, so I pulled a factor of that out. Okay, so this is how we would leave it. We don't want to put x in that final expression because that's a variable. Okay, so now one more example problem, and we're just going to set this up. We're not going to calculate the whole thing. A thin strip of material of mass m is bent into a semicircle of radius r. Find its center of mass. Okay, so now the y center of mass for this is going to be 0, and we want to find the x center of mass as the integral of x dm over m. Okay, and for this one, we are going to cut this thin strip into tiny pieces, each of which has a length of ds. And we could do this in terms of an angle. And if we measure our angle right here, we could note that this angle runs from basically pi over 2 to negative pi over 2. So we could do 1 over m times the integral from negative pi over 2 to pi over 2 of x, but wait a second, x in this would actually be equal to r cosine theta. So now we have r cosine theta times dm, and then that's it. Okay, so here's another example of where we need to turn dm into something else. Okay, so let's use the fact that lambda is going to be mass over total length, but if it's a semicircle, the length is simply going to be pi r. but that's the same thing as dm over ds. Okay, not dx, but ds. Okay? Now, the other way that we can talk about this is that s is actually equal to r theta. Okay? And this is something we'll talk about a little bit later, but you might remember this from geometry. And so that means that ds is equal to r d theta. So we're going to make the substitution that dm is equal to lambda ds, which is equal to lambda r d theta. Take that and plop that into here, and we're going to get 1 over m, and it'll go from negative pi over 2 to pi over 2 of r cosine theta times lambda r d theta. And then we can evaluate this expression to calculate the center of mass of this, okay? And so basically what we're going to have here, let's just go ahead and do this. We'll get pi r squared over m. Now the integral of cosine is going to be sine, and that has to be evaluated from pi over 2 to negative pi over 2, and that's going to be lambda r squared over m. And then sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. So that's going to be 2 lambda r squared over m. And then we just simply make the substitution that lambda is equal to m over pi r. So this becomes 2 r squared m over pi r m. So 2r over pi is the location of the center of mass. Okay, so that kind of wraps this segment up, and in the next one we're going to finish our discussion of momentum by talking about the motion of a system of particles.